All right. I think the high grade was like a high 90 something. I don't think there was 100, but like a 98 or 7, maybe even a 99. Low grade was like a 18 or something like that. Remember, if you didn't do as well as you had hoped on this one, you can do better on the final exam and replace this score. So don't lose hope unless the reason you think you did poorly is that you aren't going to be good at this stuff. Then maybe, rethink majors or something like that. Okay, so let's go through these. And then we will pick up where we left off on our interpreter. Do you leave Flippy? All right, number one, what is an instruction set and why are they typically backwards compatible with previous instructions from similar or the same architecture? So instruction set, kind of our collection of magic tricks that a particular CPU knows how to do. So that's kind of the shorthand of it. Why is it backwards compatible? Well, if it wasn't, then software that came out a year ago wouldn't run necessarily on the latest, greatest software, or latest, greatest architecture, rather, because it might use a magic trick that wasn't available now. So it has to make sure it has the old stuff still works, and maybe we add some new stuff on top of that. That's why when you look at the side of the minimum system requirements for a piece of software, it usually says, some type of CPU and some operating system, because it's relying on the magic tricks that were available starting at that CPU and the system calls that were available starting with that operating system. All right, so most people got that one, I think. 2, what is RISC and why has it made a comeback in recent years? So RISC is a reduced instruction set computer. So it's a processor that tries to imagine the number of magic tricks in a reduced form. So it tries to capture the magic tricks that will be necessary to solve the generalistic computing problem in a much smaller number of magic tricks. Some people might have mentioned some of the good and bad things about it. Compilers are difficult to write for RISC processors, and because of that, performance maybe was a little bit slower. And I remember in class we said it potentially is faster and potentially slower, so it didn't really matter what you said there. Just that was fine. Bigger thing is, why did it make a comeback? Mostly because of mobile devices. So RISC, reduced instruction set computers, kind of went away. Kind of lost to Intel or open architecture for a long time with our computers that were plugged into the wall. And now that we have these computers that we're carrying around in our pocket that are running off of battery power and stuff, we care a lot more about the efficiency of a processor and maybe less about the how optimal it solves a specific problem or something like that. So different things are important to us now, and that's why it's making a comeback. All right, questions on that one? All right, how many megabits, small b, in 3 terabytes? So megabit in 3 terabytes. I said tera, not giga, right? Terabytes. All right, so remember we have our chart, so we have to switch columns here at some point. But if you want to walk up, then walk back down. So we have 3 terabytes is times 1024 is gigabytes, times 1024 is megabytes, times 1024 is kilobytes, times 1024 is bytes, times 8 is bits. So this gets us into bits. So that's this number. Now, to get that into megabits, we divide that by 1024. So that gets us into kilobits. Divide that by 1024. That gets us into megabits. It's doing the math wrong? No, that's right. Got the right number? Yeah. Yep. That guy. All right, make sense? All right, so I think you could have also jumped the other way. You could have said 3 terabytes times 8 gets you into terabits. Then times 1024 gets you to gigabits. Times 1024 gets you into megabits. So same. Makes sense? So both ways. All depends on how you want to jump between columns. All right, questions on that one? Most people got one right, but there was more that missed it than probably should have. 4, what are the differences between the various memory systems in our computer? For example, registers, L1, L2, L3, system RAM, hard drive, and why do we need so many different options? All right, so generally speaking, the 2 things that we're looking at for comparing different memory systems is the speed of them and the capacity of them, right? Generally speaking, the closer it is to the processor, the faster it is and the smaller it is. You could also maybe mention the cost per bit or something like that if you wanted to, think about that. But if money was no object, we maybe just think about the idea of speed versus capacity. All right. So if you wanted to put them in order, which wasn't required, register is, I think I gave them to you in order, right? Register is the fastest. L1, L2, L3 cache is the guy that sits between the cores in a multiple core CPU. System memory, that's kind of our go-to model for our assembly code stuff for our ARM processor is going from system RAM into registers. And another question later on the test talks about that. And then hard drives are the slowest. Why do we need so many different ways of doing things? Well, sometimes we really care about capacity. So if you want to store your music or something like that for long periods of time, some people talked about volatile versus non-volatile memory, and there's some truth to that. Some of this memory, actually the only part of this memory that is non-volatile is the hard drive, right? That you store stuff and it just lives there until you delete it. So occasionally you want to have huge capacity, and it happens to be non-volatile. That just kind of was par for the course, and you want to store a whole bunch of stuff, but it's also much slower. So you're willing to trade off the capacity for speed because the amount of time it takes for your MP3 to load off the hard drive into system memory for it to ultimately play on the application that's running on the CPU is negligible given relative to the benefit of being able to have 3 terabytes worth of stuff on your hard drive. Similarly, when we're actually eating instructions, when the CPU is going through various magic tricks, being able to feed directly off of registers as fast as possible is going to give us the best throughput, the best performance. If we had slower system memory and we were loading that directly to the CPU, which I guess doesn't necessarily make sense given that CPUs are built in terms of registers, but assuming you could do that, assuming that the registers were built on top of system RAM speed, we would notice a giant performance degradation in our computers. And kind of I mentioned it before, but the idea that something that's closer to the CPU tends to be faster, that pretty similar example to like how cars work. If you only have to drive 1 block versus 10 miles, you can usually get there faster. Okay, because the road's shorter. In this case, we have copper wires or something, some sort of conductive metal that is the highway is built out of between multiple parts of our computer. And the shorter that is and the more conductive it is, the faster things will go. All right, questions on that one? All right. What is the decimal value? Let me write this down as we're... Okay, so I have a number 1101011. Did I copy that right? 10. Okay. So what's the decimal value of this number, assuming this was encoded in 2's complement? Right off the bat, you should notice this guy starts with a 1, which means what? We're going to be producing a negative number. Okay, any way you cut it, we're going to be producing a negative number. So we'll just remember to toss a negative sign on our final value. All right, because we know it's encoded in 2's complement. All right, so now we need to decode this. So to get something into 2's complement, what did we do? Say, so add and flip, or do we flip and add? Flip and add. So to encode it into 2's complement, we flip all the bits, then we add 1. To get it out of 2's complement, what do we do? Subtract 1 and then flip the bits, or flip the bits and add 1? Okay, so we can say, I'm going to write it again, 1 1 0 1 0 1 1 1. If we flip those bits, we got 0 0 1 0 1 0 0 0. Then we add 1 to that guy, which gives us that. And then we read that number. This is the 1's place, 2's, 4's, 8's. So we have a 1 plus an 8 plus a 32. Did I do this right? Flip all the bits. 0 0 1 0 1 0 0 0. Add 1 to that. We get that number there, right? And that should be our decoded value. This is the 1's place, 2's, 4's, 8's place, 16's, 32's place. Yeah, so this is 41. Negative 41. All right, makes sense how 2's complement works? All right, so the fact that I told you it was in 2's complement and the fact that it started with a 1 tells you we're producing a negative number. Make sense? What if, just for completion's sake here, what if it had started with a 0? And I told you that number was in 2's complement. Do you have to do any flipping and adding and stuff like that? No, it's just the number as is, right? So this is the 1's, 2's, 4's, 16's, 64, so 64, 70, so it's 80, 84, 6, 7, 87, positive 87. All right, makes sense? So 2's complement, we only need to decode if it has a 1 in the front because that means we're mapping a negative number. All right, I'll put this value back. All right, questions on that one? That one was missed quite a bit. Several people did it right. This didn't put the negative number on the front of it. So I took off 20 points. I should have done that and just watched like the reaction. All right, so that was 5. 6, what's the difference between add and add I? The I stands for add immediate. Okay, add immediate. So difference is that add adds 2 registers together, storing the result in a destination register, whereas add immediate adds a register plus an immediate value, which is like a literal number, a hard-coded number, storing the result in a destination register. Okay, so that's the difference between the 2 instructions. One lets you get one immediate involved, the other one operates out of 2 registers. Now, those registers might hold an immediate value potentially, right? But the point is that they're operating on registers specifically. Then the question is why are there 2 different ways of kind of doing adding stuff? Since we just mentioned that, well, you could just load an immediate into a register, then do the normal add to add 2 registers together to get your sum in a destination register where the immediate was involved, but you had to load it into a register. Part of the rationale for this is going to be speed, right? That's one less instruction that's needed. Because we would have to do a load instruction to get the literal value into a register and then do the math. So we have an extra instruction there anyways. And then the other argument you can make is also, and this is probably the better argument, realistically speaking, is the resources, registers themselves. We do have a fixed number of registers. We have 31 usable registers in ARM. The 32nd one is that zero register, but we have 31 usable registers in ARM. And, in our little examples, we might think, okay, well, it's unlikely we would run out of all of them. But as a problem gets more and more complex, as your compiler is producing zillions of lines of things, and you have a whole bunch of values that are in the same, if we compare this to high-level languages in the same scope, you might be playing with fire when you deal with the number of registers you actually have available to you. So if you could save a register, not have to utilize a register as part of an instruction, and you have the net gain of having one less instruction, it's gold, right? All right, so that's the real argument there. Difference between them is one lets you do an immediate value and one doesn't. The value of it is that we use less resources and gain performance. Questions on that one? Okay. Explain what the instruction does in detail. Okay, I want to write this one down. This one was missed a lot, which surprised me, because I'm positive I explained it perfectly. And I think there was things in the book that had you like do interactive exercises with this kind of thing, right? So this is a load instruction, right? Okay, so it's a load and unsigned. We have a destination register. So X1, we're loading something into that destination register. What are we loading? We're going to go to our base address X2 and take 40 steps forward. So we're going to a place in memory and then taking an offset from this. This is an array, and we actually see evidence of that since the ARM instruction set is newer than the C programming language. We see the kind of the influence that C had on the syntax here, where they put the little square brackets in here that says, hey, this guy works like arrays work. So this says go to the base address, and the base address happens to be stored in X2 in this case. So whatever X2 in this case will hold an address. Go to that address, take 40 steps forward in memory. That's a value. Store that value in X1. Make sense? Okay, so the thing that was just missed quite a bit was just this idea that this guy represented an offset from a base address. Now a couple people did it kind of backwards, where they said we're going to store into this memory this value. That's more okay. At least you understand the base address dealy flippy thingy. That's the most important thing, is that this is a kind of a go-to move in computer science, is that we have things in contiguous memory, and we start off with a base address and work with an offset from that. All right, questions on that one? What are the binary and octal versions of the hex value ABC123? Okay, this one became much easier if you remember the trick. If you didn't remember the trick, this might have been somewhat of a nightmare question. So what we're going to do is I'm going to rewrite ABC123. So I'm asking for what? Binary and octal versions. Okay, so I'm going to rewrite this guy. First, I'm going to convert it to binary. Okay, because I can use the trick that lets me go from hex, base 16, to binary. So I'm going to rewrite the A as a 10. I'm going to rewrite the B as an 11. I'm going to rewrite the C as a 12. Then we have a 1, a 2, and a 3. All right, now I'm going to write the 4-bit version of each of those numbers. Okay, so this is a 1010. That's a 10, right? This guy is a 1011. That's an 11. This guy is a 1100. That's a 12. This guy is a 0001. It's a 1. This guy is a 0010. That's a 2. This guy is a 0011. That's a 3. And you squish all those guys together, and you have your binary. That's your binary number. All right, so that is 101010111100001000100011. Hopefully I didn't copy that.
Say that one more time.
No. Actually, as I was doing that, I was remembering back to an episode of Futurama where Bender was doing a play all in binary. Yeah, if you don't know what Futurama or Bender is, then that joke was right over your head.
Can you do a Bender voice, though?
I'd have to hear it again. I'm pretty good at voices, actually. But so my guess is yes, I could with some practice. I'd have to remember I haven't seen Futurama in a while. Okay, so now we have the binary version of that guy, right? Okay, so that's part of the question. That answers that. Now, to get us the octal version, you had to know the other trick. That is, for hexadecimal, we can represent the legal values in hexadecimal are 0 through 9, A through F. Or if you want to just deal with it in numbers, it's 0 to 15, right? And we need 4 bits to represent the number 0 to 15. So 1111 is a 15, 0000 is a 0. Everybody's happy. Octal, the legal octets is the official name for them, is 0 to 7. We need 3 bits to do that. 1111 is a 7, 0000 is still a 0. So what I'm going to do is I'm going to go through and I'm going to break these guys up. Here, I'm just going to, just for the sake of completeness, so I have both answers up here, I'm going to break these guys into little groupings of 3. All right, and then I'll write the equivalent. So 101 is a 5. So 1 in the 4's place, a 1 in the 1's place. 010 is a 2. 111 is a 7. 100 is a 4. 000 is a 0. 100 is a 4. 100 is still a 4. And 011 is a 3. So the octal version is 527404443. And this is the binary version. Read it as an exercise for the reader. And it's actually a true statement because my close vision isn't as good as it used to be. So that it becomes pretty sketch reading those close values next to each other. All right, questions on that one? So if you knew, you all knew the trick. If you remembered the trick, this one wasn't shouldn't have been very hard, right? Your chances of a mistake would be that you made like a little stupid nibble problem. You know, you wrote a 9 instead of a 10 or something like that. But you showed that you knew the pattern. You just made a dumb mistake up here, which then caused this thing down here to be broken. Those aren't huge deals. But if you completely didn't remember the trick, yeah, this one would have been rough. you would have used some, algorithmically not rough, but you would have been dealing with some pretty large numbers because you probably would have converted it to decimal first and then gone from decimal to binary and decimal to octal. And that decimal value of ABC 123 would have been big. Okay, so we're good on that one. What is the result of performing a bitwise XOR on that stuff? So bitwise says we compare individual bits, and we have a 11011, 110111010, and then we have 00111110. I think I copied those right. All right, so remember, a XOR is one or the other, but not both. So whether you call it XOR or XOR, I've always called it XOR, but now I've adapted to XOR because it's fun to say, I think. But it's one or the other, but not both. That's what differentiates a XOR from an OR. OR is one or the other or both. XOR is one or the other, but not both. It's an exclusive OR. So 1 XOR 0 is a 1. 1 XOR 0 is a 1. 0 XOR 1 is a 1. 1 XOR 1 is a 0. 1 XOR 1 is a 0. 0 XOR 1 is a 1. 1 XOR 1 is a 0. 0 XOR 0 is a 0. So that should be your final number thingy. 111001000. Make sense? All right. Questions on that one? So that one should have been pretty simple as long as you knew what XOR did and as long as you understood what bitwise operations are. If either of those fell off the face of the earth for you, it would have been not good. but if you knew those two sizes, it was a pretty simple question. Let's see. Convert the base 19 value, GH46, into base 3. Ay. All right, GH4, GH46. I tell you what, my close vision's gotten so much worse with contacts, but I can see like Superman at a distance. It's awesome. But I can barely read stuff up close. It's really pathetic. All right, now I said this is base 19. All right, so this guy is currently in base 19, and that needed to be given information, right? Is that a legal base 24 number? Yeah, absolutely. So I had to tell you what base this guy was in to begin with. All right, so we're going to go ahead and convert this guy to decimal first. Okay, and then what are we going to do from there? Then we're going to convert it into base 3. So this proves that you have to do both patterns, and it also makes you prove that you understand that the patterns don't require you to deal with one of the cool bases, octal or binary or hex or something like or decimal, right? It doesn't matter what the base is. All right, so I'll just spread these guys out a little bit. GH46. And then now I'm going to rewrite those. What letter of the alphabet is G? 16. And what was H? 17. All right. 4 and 6. Oh, and if you didn't know how to get these numbers, you just write the whole alphabet out, and then you count the numbers. So an A is a 10, a B is an 11, a C is 12, until you get to G and H. Then you put the number underneath that. Okay.
Just remember that hexadecimal stops at F, which is 15.
Yeah, but at least I have problems picking up the alphabet in the middle. It seems difficult. Like I always have to sing the song. And then I get excited and I want to finish. So
the middle doesn't start until I. Before I, it's still the beginning.
Yeah. See, I really think they should really do some experiments on me. I feel like I'm like a 1.5-year-old in my head. It's just the things that will entertain me. It's really, really. I would call it pathetic. My wife would call it cute. So I guess pick your poison there. All right, so now this is base 19. So if I'll just write these. I'm gonna rate it first, and then spread it out. So this is 0, 1, 2, 3. So this is 19 to the third power here. This is 19 to the second power here. This is 19 to the first power here. And this is 19 to the 0th power here. All right, so 19 to the third power is 6859. 6859. 19 squared is 361. 19 to the first power, I can do that one. That's a 19. And 19 to the 0th power is a 1. So once again, the far right place is always the ones place, no matter whether you're dealing with base 2, base 3, base 5, base 13, base whatever. All right. So now we're going to do the math. So this is going to be 6 times 1 plus 4 times 19 plus 17 times 361 plus 16 times 6859. Okay. Copy those guys. So that gets me that number in decimal. So 115,963 in decimal. All right, so now once I have the decimal, what base am I going to? Base 3. All right, so what I'm going to do is I'm going to just create another slide here. 115,963, 115,963, base 10 to base 3. So 115,963 divided by 3. 115,963 divided by 3 gives me 38,654. 38,654, and that's remainder 1. Am I doing my math wrong there? 38,654 times 3 is 962. Yeah, remainder 1. And then this guy divided by 3. 38,654 divided by 3. That's 12,884, remainder 2. 12,884 with a remainder of 2. Then 12,884 divided by 3 is 4294, remainder 2. What's the number? 42. Is it 4294? Is that what I said? Remainder 2. 4294 divided by 3. 4294 divided by 3 is 1431, remainder 1. 1431 divided by 3, 477, remainder 0. $477 divided by 3, 159, remainder 0. $159 divided by 3, 53, remainder 0. $53 divided by 3 is 17, remainder 2. $17 divided by 3 is 5, remainder 2. $5 divided by 3 is 1, remainder 2. $1 divided by 3 is 0, remainder 1. Then you read your answer from bottom up. So this is 1, 2, 2, 2, 0, 0, 0, 1. Uh-oh. What did I hit? 0, 0, 0, 1, 2, 2, 1. That guy. Yeah. Is that the right one? Felt right. All right. All right, that's all the questions. So how is, well, any high-level questions about the exam? If you have specific questions about how I graded something, just come up at the end and if you think I gave you or took off too many points, I'll give you some back. If you didn't think I gave you, or you think I took off, I gave you points that you didn't deserve, I'll take them back too. Have you ever had a teacher do that?
No.
I did have a teacher do that once. Yeah. I went up and asked him a question about something, and I got 2 points back on one question and lost 3 more points on another question. It was a net loss of a 1. I should have kept my trap shut. I won't take points back. If I misgraded your test, that's my own fault. It was your lucky day. But I never make mistakes, so it's chances of that are nil. All right, we're good on the exam. All right, and so these are in the notes and saved, so it should update on the slides and stuff. Okay. I already mentioned, remember that if you did crappy on this exam, you can do better on the final and replace this score with that. I'll just re-put this thing up here. Remember, hackathon, November 17th, 8 a.m. to 8 p.m. Required in my classes. We're doing it on machine learning. So if you haven't already signed up, email Professor Josh Locklear and tell him you want to sign up, and he'll get you on the list. I think we are doing a, he checked with me earlier today to make sure the night was fine. So I don't know if it's 100% solidified, but I'm pretty sure it's going to be the Monday before that, whatever that is, Monday the 13th or something. At 6 p.m., we'll do a little boot camp for, introduction to the machine learning stuff. So if you've never done that stuff before, maybe put in your calendar for Monday at 6 p.m., whatever that date is. Is it the 13th? Sounds sort of right to me. Monday the 13th? 12th? Monday the 12th. I said it seems sort of right. So Monday the 12th, 6 p.m., I'll go through some crash course stuff on machine learning. Okay, so let's keep trucking. We were working on our Android implementation of our ARM interpreter dealy flippy thingamajiggy, right? All right, so let's just open up Android Studio. Oh. All right, so there's some things we're going to have to start considering here. I want to see where we left off, but we're going to have to start considering how do we represent system memory. So coming back to what I was talking about a few minutes ago, when we start talking about the architecture of a CPU, our go-to moves, even though we have all those caches and stuff like that, those are really optimization tools when we deal with using L1, L2, L3 cache, and a lot of times they're used in conjunction with an operating system. Okay, so we're not going to focus too much on the optimizations. What we're going to be looking at is kind of our bread and butter of dealing with processing assembly code, let's say. So what's the life cycle of, well, here, let's ask it this way, just so we understand how things get to the point that we're emulating here. What happens when we double click? All right, so you have Chrome installed in your computer or Microsoft Word installed in your computer, and you double click on that icon. What happens? What's the steps that occur? What magic is happening under the hood? Where is Chrome or Internet Explorer or Microsoft Word? Where are those files actually stored? Hard drive. Okay, so we have 3 players here. So when we double click, files are loaded from the hard drive into where? System memory. Yep. It's called system RAM. All right. Now, I'm going to actually go ahead and put little double quotes around this guy. when I say files? Are all the files associated with a program loaded into memory? The short answer is it depends. The even shorter answer is not anymore. Okay, but that's more of to fully define double quote files, double quote, it's an operating system concept, right? So look for that in your 350 class, where they'll talk about different ways of memory management and how frames work and paging memory schemes work and stuff like that. How do you take, generally speaking, what are we doing? You're loading the first portion of the application into memory, and then more pieces of the application might get loaded into memory as needed, instead of loading your entire application into memory that might be a 1.2 gig install or something like that. That makes sense? Even though we technically do have enough RAM today where we probably could handle that. All right, but some files are loaded from your application into memory. That's good enough for us in here. Okay, now what's the next step? Because effectively, when we've double clicked, who are we talking to? When we double click on an icon, who are we talking to?
Yeah.
The operating system. We're asking the operating system to do some stuff for us. And generically speaking, we're saying, I want to run this program. Okay, and we know that running the program ultimately is going to involve the CPU executing some instructions, right? Okay, so what happens under the hood? We go and find the files on the hard drive. We load some of those into memory, and then from there, instructions are initially loaded into registers. Okay, this completely bypasses the idea of cache. That's definitely used in part of this to optimize that speed as things are leaving RAM and getting onto the CPU or getting onto the registers, and we can kind of preload them into cache. They're sitting a little bit closer to the registers, so they're kind of ready to jump, get in there quickly. So optimization thing, but at the high level for us, hard drive to system RAM to registers. Make sense? And then from registers, the CPU starts feeding based on those instructions. If we say, we use the add instruction, it's going to tell us, here's the 2 registers we want you to add. Here's the register we want you to put the result. CPU will do that magic trick. Make sense? Okay. So instructions are initially loaded into registers. CPU eats. All right. So when we're building, when we're building kind of an emulator, an ARM CPU emulator thingy-majig stuff, we have to imagine how we're going to represent those different pieces. Okay, and this is going to allow us to really drive the point home of base memory addresses and offsets and where our stack data structure comes into play. Remember the stack data structure from 300?
Love it.
Yeah, and the whole thing was like, oh, isn't that just used for towers of Hanoi? It actually is used for real things. Okay. Actually, not all of you have had 300 yet. A couple of people are trying to compress because they were transfer students or something, so need to get classes in a little bit different order. So things will be interesting. All right, but in any case, what happens when you double click? This is what happens. All right, so we go into our program here, and let me kind of remind myself where we. Oh, I put an error in on purpose.
Or we never finished writing out. Yeah, you didn't have it.
Okay, good. Finish mapping here. All right, hold on, I got. Oh, it's really getting pathetic. At what point am I going to have to get readers with contacts? That's not cool, right? I just got out of glasses a year ago, so I don't see as well, but I can wear cool sunglasses. So where do it's still finishing this Gradle update. All right, so let me just remind myself what we're kind of doing here. So we have this thing called, we were testing our lookup instruction thing. So we have this thing that we built called the binary value, right? And our binary value is our way that we're going to kind of represent our registers. It allowed us to create a binary value that had a number of bits associated with it. So we're going to say I want an 8-bit space or a 16-bit space or a 32-bit space. This is a convenient object-oriented approach to how can I quickly get a value that's padded to the right number of zeros to represent the actual bit space I'm working with. All right, so how am I actually storing my bits? I'm keeping track of 2 pieces of information, the total number of bits I'm allowed to have, which I actually probably don't even need to store since I'm building my array to be that size, but whatever. And then the bits array itself, and we're storing those as bytes because that's the smallest representation we can find to hold zeros and ones. So other than just trying to be as efficient as possible, we could have stored them as ints if we wanted to. But now we have a 32-bit representation of a 0 or a 1, which is wasteful, but who cares? We have plenty of RAM. But we tried to be a little bit optimal, so we're just storing them as 8-bit values to store a single 0 or a 1. Called the bits, so we're going to fill up our bits array. It's going to be a new byte array of size num bits. And then I showed you, if you hadn't seen it before, we have a fill method that belongs to this class called arrays, which has a bunch of helper functions for doing things to arrays. And one of them allows me to pass in the array I want to fill and the value I want to fill it up with. Okay, so this allows me to go ahead and create a bit space of zeros, effectively. All right, and then we gave ourselves a display function in here for displaying that stuff. We're just showing us what it looks like. Then we also gave ourselves a second constructor here for our binary value. This guy takes in a string binary number, so our binary number representation, and goes ahead and we call upon our other constructor. So the constructor that lives inside of this class, the one that just takes in a number of bits, let that guy go ahead and build up our initial bit array, right, with a bunch of zeros, so the correct number of zeros. And then we go ahead and overwrite that guy with the right zeros and ones. Now this does presume that if I'm trying to build a 8-bit register or a 16-bit register, that the binary number I pass in here is that bit size. You know, like if I'm trying to represent the number 101 in 8 bits, I technically need 5 zeros followed by 101. This would require me to pass in that, as opposed to me passing in this and trusting it'll set it up right. I would need another constructor that took in a number of bits that would allow me to pass in this guy and say I actually want to represent that guy in 8 bits, so do the padding. All right, so we could build another constructor if we wanted to give ourselves even more flexibility. All right, but for right now, we'll leave it this way. So we're going to go ahead and we're going to call upon, I commented these out because we are showing you, many of you probably have not seen how a object can call his own constructor, one of his other constructors before. So I introduced this when we looked at this. So historically, if you've seen object-oriented programming and you've seen the inheritance model, you might be familiar with an object calling upon his parent's constructor to accomplish something. Kind of let my parent do some initial setup and then I'll differentiate myself from that. In this case, we're calling one of our other constructors to do some of the initial setup and then we're further differentiating ourselves with this one. All right, so I'll call my other constructor that was up top that builds my array, and then I'll go ahead and fill my array up with the correct values, toggling between a 0 and a 1. Okay, so that's what our binary value dealy thing is there. Then we have this thing called an ARM instruction. And so this was our mapping. We were looking at the Xi book last time, and we had the different ways that we're representing our spaces. So like the instruction is an 11-bit value, so on and so forth, right? So an ARM instruction is going to be represented as a 11-bit instruction, followed by a 5-bit destination register, followed by a 6-bit. This was our shifts that I think the second section showed an example of that, but the first section just said ignore this, right? And then your source 2 and your source 1 for your other registers that are playing into this. All right, so we're going to represent our ARM instruction as one of these guys. So the default constructor for ARM instruction just builds our binary values up here. Here's an example where we are going to actually want it to fill that guy up with some stuff. So this is probably where we're going to come in a few minutes and add some stuff here, where we're going to have an instruction, we're going to have a destination, we're going to have a source register and have our first and second source registers, and then actually get them loaded into our arrays. So the very first thing we would do in here is go ahead and call upon the constructor that initializes our arrays, right? So that'll be this. So that'll go ahead and initialize all these arrays, and then we can further distinguish between those by loading these values into our binary values. Okay, but we're going to have to put a mechanism into our binary value to load an instruction after the fact in, because right now we don't have that mechanism. So we'll come back to this here in a second. Here in AR map, this is where we have our current error. We were talking about how do we represent our registers. So we have an X1 through X31, is that right? Because X32 is the 0 register. Actually, I don't even think it's called X32. Isn't it called XZ?
No, it's X31.
It's called XZR.
Oh, X0 is what would be X0, and that's XZ.
No, X. I think maybe, but I thought it started at X0. X30.
Oh, for our numbers here, is it?
I thought there was an X0.
Well, the 0 register is on one of the two ends. So it's either, so what would be X0 is XZ, or what would be X31 would be XZ. Where does it list our registers here? Here. ARM registers.
Might this be a late thing?
The X thing, possibly. I guess it doesn't really matter. This is going to be only a subset of one anyways. So let's just go by whatever the book says for registers. Let's see if ARM v8 lists the available registers. Yeah, see, we have 32 and 64-bit registers in that, so they've added in the word registers. But it looks like X0 is the first real register, which means that X31 would be our 0 register. Let's just roll with that. All right, so we're creating a mapping here for our registers, because our registers, if you remember from the book, even though we call them, so this is a data representation type language, right? Even though we call it X0, X1, X2, X3, under the hood, it actually uses a numeric representation, a 5-bit numeric representation of that register. So I think wasn't the numeric representation the actual number that was there? So X0 would be 0, 0, 0, 0, 0, and X30 would be what, a 1 in the 16, a 1 in the 8, so on and so forth. I think that's how it represented the registers. We can just jump to that real quick here. Yeah, here's that XZR. That's the 0 register. I think it's the one right before this. I'm looking for the one that has the that shows like the instruction, 11 bits, that kind of stuff. Representing instructions on the computer. I think this sounds right. Yeah, so like X21, this is the ones, place, twos, fours, eights, 16s. So this is 16 plus 4 plus 1, that's a 21. All right, so the register itself will have a binary, a 5-bit binary value that is indicative of, well, that matches the decimal value associated with the register name. That's how it's storing it. Okay, so what we're going to do is we're going to create a collection of our register names first. So here's our private thing. And actually what I'm going to do is we're going to do this the cool kids way, because I don't want to type all this stuff. So we're going to have our registers here. And this is going to be a new string array of size, and we're going to give ourselves 31 registers. This is the 32nd is for the 0 one. All right, and then we're going to have a private static string array register bin map. This will be a new string array of size 32. All right, so now these guys are currently set up as static though. That's why it's not. See, if I had a constructor for this guy, then I can go ahead and initialize these, and I think we might want to do that to save ourselves some headache. This isn't gonna, well, let's just do it. So we're gonna give ourselves a public AR map, and this guy's job is to initialize anything that needs to happen in order for AR map to function. So what I want to do is I'm going to programmatically build up my registers and programmatically build up my register bin maps. So those guys are filled with the correct values. Otherwise, I'd have to hard code in X0, X1, X2, X3, and then hard code in, you know, the register 0000 and whatever, 5 bits. Yeah, 5-bit version of all the different numbers, which would start not being fun, I guess. I guess it wouldn't be that horrible, but whatever. So we're going to write the code to do this anyways. So I'm going to go ahead and fill up registers with X0 through X31. So we'll say for int I is equal to 0, I is less than 32, I plus plus. And now since these guys are static and I want to be able to access them through these static functions, I'm going to go ahead and say AR Shift AR map dot registers at bucket I is equal to X concatenated with I. So it'll fill it up with X0, X1, X2, X3, X4, so on and so forth. All right. But now at the same time, I want to fill up register bin map with the 5-bit string representation of I. 5-bit binary, the string representation of the 5-bit value I. So I need to make sure it's padded out to that. All right. Now, what I'm going to do is in binary value, I'm going to give myself some helper functions here. Actually, I can do it local. So I have a lookup instruction. Did I give myself anything else in here? That's a decimal to 11-bit binary. So I'm going to go ahead and give myself a similar function here, decimal to 5-bit binary. Private static string decimal to 5-bit binary. All right, so this guy will ultimately return for me a 5-bit representation of a string. Now, one thing I want to do here is I'm actually going to write a more generic version of this so I can leverage it for my other guys here. So I'm going to create a private static string decimal to n-bit binary. And I made this guy private. And this guy is going to take in an int opcode and an int n for number of bits. Let's just spell it out, num bits. And I'm going to put most of the logic that I had in here. So I do my conversion to decimal, but then instead of automatically padding it to 11, I'll pad it to num bits. And then it's going to give me the answer. So this is just a generic version of that function that converts any decimal number to an n-bit representation of that number. Presumably that I can't say give me the number 4023 in 2 bits. That won't fit. Right? It doesn't fit in 2 bits, so it's got to work. Okay, but this will make it convenient for us. So if we have this generic function like this, then what we could do is we can write the 11 and the 5-bit version. As a one-liner. So the 11-bit version, we'll go ahead and return ARMAP dot decimal to n-bit binary, passing it our opcode, and then passing it 11 bits, like that. Similarly, for our 5-bit one, we'll do the same thing here, but pass it a 5 for a number of bits. Make some sense? So I gave myself a generic function that allows me to convert any decimal number to its binary equivalent and pad it to some number of bits. And then I leverage that with my decimal to 5-bit binary, decimal to 11-bit binary, in case it was beneficial for me to remember that registers are 5 bits and operations are magic trick names are 11 bits, so on and so forth. All right, so now once I have that up here in my ARMAP constructor, as I'm filling up my registers, I can go ahead and I can say ARMAP.registerBinMap at the same bucket. I is going to be equal to ARMAP.decimal to 5-bit binary of I. So I'm creating two collections, a collection of all my registers names, X0, X1, X2, X3, blah, blah, blah. And then I'm creating a second collection that is going to be a collection that is the 5-bit representation of 0, of 1, of 2, of 3, of 31. Make sense? So I'm just giving myself a whole bunch of little helper functions to do some little conversion things like that. We're out at 25, right?
Yeah.
Yeah, so we're good. Not open. All right.
The hard is when you have it closed and you're walking and a little bit seeps out. And so you've just got this ring.
Well, that means you filled it too much.
There's that stuff.
There might be truth to that. Okay. So this AR map thing is going to kind of be my little toolbox that I'm going to use for grabbing anything ARM related. Oh yeah, that's a clever name, right? AR map. Didn't I say that last time? I'm still impressed by it. Was it my idea? Or was it somebody else's idea?
It's your idea.
Ha! Ha! All right. So this guy's going to be kind of my toolbox when I need something of a certain size so I can work with it. We're having all of our little ARM stuff in here. We can make arguments that there's better ways of organizing this stuff or something like that. But since we're building this very organically, let's say, we're going to say this is good enough for what we're trying to accomplish. Okay. So our AR map is going to do this wherever we actually build our ARM interpreter-ish. It's kind of an interpreter, I guess. We're going to have to create an instance of AR map, at least to get those guys initialized. I could choose not to call it AR map like this. I could say, like, instead of using it like a constructor, like I'm using right now, I could instead just make this a static function called initialize or something like that. So if I make it a constructor like this, when I want to initialize something, I would have to do something like this. AR map. Actually, I don't even need to create an instance of it. So I could just say new AR map like that. Oh, it actually makes me store it in something? That kind of sucks.
Well, you're not doing anything.
Well, I am doing something, though. My constructor has all sorts of logic in it. It just doesn't rely on me building a object, but it does, because it does build an object, it's going to make me say something like AR map AR is equal to that, even though I have no intention of ever using AR.
I think it should be fine enough.
Well, one would have thought that would be true, but this guy, constructor is written correctly.
Mine's not giving me.
Did it not like that I have parentheses around?
I'm guessing, yeah.
Very strange. Yeah, so that has to do with how the language is designed. Something that starts off with a parenthesis isn't allowed to stand on its own. It must be part of, so this must be called like a paren statement or something like that. And it needs to be stored in something. So this is probably part of the lexicographical syntax of the assignment operator.
So you could probably use that to call a method of AR map.
Well, I made them all static.
Right, but if you didn't have a static method, if it was an instance method, you could probably use that to call it without having to define a specific instance.
Well, I'm just going to do this because I don't like that constructor thing. That's poor form. So I'm going to say AR map. I'm just going to call this guy init. Static void init. So then wherever we want to actually initialize this, we can just say something like AR map.init. and it looks legit. Instead of just a random new AR map sitting out there where we don't actually need to create new memory. So it's probably a poor use of the constructor anyways. So this makes more sense. This isn't where we'll put it, but that's where it would end up going. Okay. So we have our mapping thing set up. What we need to figure out next class, and I'll probably do a assignment related to this over the weekend, is how are we going to represent our registers? We're going to start thinking through our interface, because imagine we have a couple of instructions, right? We need to be able to load values into our registers. So if I say add x1, x2, x3, what I'm saying is add the contents of x2 and the context of x3 and store the result into x1. I need to have some interface that allows me to add the values to x2 and x3. Put a number in there. If I want to add 5 and 3 together, I need to be able to put a 5 into x2 and a 3 into x3 so that I can add them together and get the result. All right, so we're going to need an interface for that. We're also going to need an interface for our memory, how we want to represent memory so we can implement load and store instructions. Questions, comments, concerns, bribes? All right, I will see everybody on Thursday. Bible homework is up and it is corrected. For those of you who tried to work ahead, there are a limited number of chapters in Titus. Okay, but I still expected you to do Titus chapter 4. I don't. It's the next chapter in Acts instead. All right, I'll see everybody on Thursday.